Okay, so we're going to start the new chapter today on integral calculus. So for now, you can think of this as a separate chapter, just on its own. Later on, next week or the following week, we will then link the integral calculus to the antiderivatives. Okay, but that comes a bit later. For now, please think of this as a new chapter, so don't mix it up. And then later on, we'll see how the antiderivatives fit in. Okay, but don't mix them up just yet. Okay, so integral calculus. Okay, so this is like the sister chapter to differential calculus. So at the beginning, we do differential calculus. Now we do integral calculus. You put the two together, and then you just get calculus. Yeah, we'll see later on how they're linked, but for now, again, just think of it as a separate chapter. So the way integral calculus came about is by the finding the area underneath a curve. Okay, so some time ago, someone thought of how do we find the area underneath the curve, and then that led to this integral calculus. Okay, we call that the area problem. Okay, so let's say we've got a curve given by some function f of x. So we have x and y, got our normal axes. We've got some function, it doesn't matter what it's doing for now. Okay, so what we want to do is find the area underneath this curve from some a to some b. So over this interval from a to b. Okay, we've got this, this region here. Okay, so if I give you a function f of x, okay, that makes up this curve. Your starting point A, your ending point B, what is this area? Okay, so we call that the area problem. Now, there are a number of ways of doing this. So we start off with the simplest way, which is called the Riemann sum. Okay, later on, when you do more advanced mathematics, later on with engineering maths, you'll see that there are other ways of doing this. Okay. So for now, we're going to do the simpler one, and then later on, you'll do the more advanced stuff. Okay, so what we do is we imagine taking this region and cutting it up into a lot of rectangles. Okay, so I'm going to redraw the picture. Okay, so we've got our curve like this. We've got our starting point A, our ending point B. Again, this is f of x. Okay, we take this interval from A to B, and we cut it up into pieces. Okay, and then we form rectangles where the width is just a little segment of the interval, and the height of the rectangle is given by the function value. Okay, so here we get one rectangle, we get another one, okay, and we end up with something like this. Okay, so here we just have a few rectangles, with a little width we call delta x, and the height of each one is given by f of x at that particular point. So let's say at this point here. So we know how to find the area of a single rectangle. So let's say this one here. Sorry. Okay, so the area of that rectangle there is just the base times the height. Now we've got a number of rectangles, so the area is just going to be the sum of them. But here we have a bit of a problem. So I'll just zoom in here. If we have a finite number of rectangles, there's going to be some error, okay, in this area. So let's put that in red. So here we see this rectangle goes above the function. So it goes a little bit above. Over here, it goes a little bit below. And then over here, it goes a little bit, and then here, maybe there's a little bit there. So these red regions, that's the error. So the rectangle is either above the function, and the area is bigger than what we wanted. Sometimes the rectangle over here is below the function, and then the area is less than what it should be. So how do we fix this problem? We fix this problem by making the rectangles smaller and smaller. If we make these rectangles smaller and smaller, then these error bits, so this red bit over there, this red bit over there, that also gets smaller and smaller. Okay, so just to show you the process. Okay, so I'll redraw it again. Okay, again, we've got some function, and now we use very small rectangles. Okay, so I won't draw all of them, just a few there. We see that if the rectangles get smaller and smaller, we see this error gets smaller and smaller as well. There, a little bit there, a little bit there. Okay, the error gets smaller. Now, what we do is we take the limit as the number of rectangles goes to infinity. So, if we take the limit as the rectangles go to infinity, the little widths of the rectangle, the base of the rectangle, will get smaller and smaller, and so the error gets smaller and smaller. And in the limit, the error goes to 0, and we get the exact area underneath. Okay, so how do we write this down to do calculations? Okay, so the first thing we need to do is define what the width of the rectangle will be. So we've got our starting point A, we've got our ending point B, so the distance from A to B, or the total width of that interval, will be B minus A. So delta x will be B minus A over N, where N is the number of rectangles. So if you take the full interval from A to B, you divide it into N parts, that's going to be the width of one of the rectangles. Okay, so that's the first step. The second step is finding the x position of each of these rectangles. So here, at this point here, there, that's going to be A. Right over here, that's going to be B, the x value. But what about in between here? What are those x values going to be? So if we zoom in here, we're starting at A. And if we go to the next rectangle, you can think of it as being a little hop. So from here to here, we hop there, then hop there, then hop there. And we get each of those x positions. So how do we find what the x position is given how many times we hopped? So the first one, at A, it's just A. What's the next one going to be? We've moved a distance, delta x. So it's going to be A plus delta x. If we go one more time, we've hopped 2 rectangles, so that x position will be A plus 2 delta x. If we hop 3 times, it will be A plus 3 delta x. And we just keep hopping until we get to the end. So we can write that down as xi, for the rth rectangle going along, is going to be A, our starting point, plus I delta x, where I is the number of times that we hopped. If we hopped 0 times and we're just at the start, I is 0 and we get A. If I is 1, we've hopped once, so it's A plus delta x. If I is 2, it's A plus 2 delta x, and so on. It goes all the way up to that last rectangle there. Okay, so we've got the x value at the base of the rectangle. Given that x value at the base, we can use that to find the height. That's number 3. The height of the rectangle is going to be f at the base. F of xi. Okay, so that's going to be our height. So delta x, that's the base. F of xi, that's the height. Okay, that's all the information we need to find this area. So the area is approximately equal to, so we're not going to do the limit yet, so it's approximately equal to the sum from I equals 1 to n, because we have n rectangles, base times height. or height times base. So it will be f of xr delta x. Okay, so why are we doing the sum? Each term in the sum is one rectangle, height times base. We need to sum them up, and then that gives us the full approximate area. Okay, but again, it's just approximate because we haven't taken the limit yet. This is called a Riemann sum. Okay, so it's just a sum. The guy who came up with it was Riemann. We call it a Riemann sum. Okay, if we want the exact area, we take the limit. Like I said, you make the rectangles thinner and thinner. You have infinitely many, you get the exact area. So the area is now equal to, not approximately equal to, the limit as n, put capital N goes to infinity, the sum from I equals 1 to n, f of xr delta x. Okay, once we take the limit, we don't call it a Riemann sum anymore. We call it a limit of a Riemann sum, because we take the limit, or we call it a Riemann integral. Okay, so these are the steps that we take to find the exact area underneath the curve from some point A to some point B. So when doing the calculation, you follow these exact steps. So the first thing we do is we find the base, the width of the rectangle, then we find the x value at the base, we find the height, we find the limit of the Riemann sum. Okay, let's do a couple examples just to show you the process. Just a little bit of advice here. When we're doing these sums, you need to know the following sums. Okay, these won't be provided, you will need to know them. Okay, so I equals 1 to n of just a constant, so like 1. So if we have 1 plus 1 plus 1 plus 1, n times, that will just be n. Okay, so you've seen this before. Okay, then we have the sum from I equals 1 to n of I. Okay, what's that going to be? Okay, 5 points to whoever gets it. Sorry? Okay. Anyone? Okay, so this will be n plus 1 over 2. Okay, I'm a bit worried about the laughing. Did you not know that? Have you not done that before? No. Okay, I'll just write these out and then we'll go through them properly. Okay, the sum of r squared, so you need to know that, and then the sum r equals 1 to n of I cubed. Okay, so I'll leave the r squared one, we'll get to that later. I'll start from the beginning, since everyone looks a bit lost. But the sum of r cubed, that's going to be n plus 1 over 2 squared. Okay, so let's just go through this from the beginning and then we'll introduce these. Okay, so the sum of I, so what we want to do is take 1 plus 2 plus 3 plus 4 all the way up to n. We want to see how to do that. Okay, so let's do a quick proof on that. Okay, the sum I equals 1 to n of I should be n plus 1 over 2. Okay, how do we do that? Let's call this sum S. Okay, S for sum. Okay, I hope you're writing this down if you don't know where this comes from. So S is equal to 1 plus 2 plus 3 plus 4 plus ... plus n. Okay, everyone should be writing this down because no one managed to answer that question. Okay, so that's the sum, and we write it from 1 up to n. What we're going to do now is rewrite it, but in the reverse order. Okay, no problem with that. You can have a sum going forwards, backwards, you get the same results. So here, s is equal to n plus, now we're going the other way. So it's going to be plus n minus 1, plus n minus 2, plus dot dot dot, plus 1. Okay, so all we're doing is we're rewriting the sum in reverse order. We get the same value because it's a finite sum. Now, what we're going to do is add the two together. So let's add them. So s plus s, that's going to be 2s. 1 plus n, that's n plus 1. 2 plus n minus 1, that's n plus 1. Okay, 3 plus n minus 2, that's n plus 1. Okay, I hope you see the pattern. Plus dot dot dot, and then the last one, n plus 1, that's n plus 1. Okay, now we have a whole lot of n plus 1 terms. How many do we have? Well, we had 1 for each of these terms in the sum. We had n of them, so here we also have n of them. So to s is equal to, we have n, so we can write it as n plus 1. Now we don't want 2s, we just want s. So we can divide by 2. So s is equal to n plus 1 over 2. Okay, which is what we wanted to show. Okay, anyone confused with this? Okay, so let's try do a simple example. Okay, so we have f of x, 3x minus 1 on the interval 1 to 2. Okay, so we've got our function, we've got our interval there from 1 to 2. We would like to find what the area is. So we follow those same steps that we had before. We calculate our delta x, we calculate our xi, f of xi, and then we find that limit. So, delta x, that's going to be b minus a over n. So 2 minus 1 over n, that's going to be 1 over n. Okay, what about xi? Okay, that's going to be a plus I delta x. So it will be 1 plus I over n. Okay, do you mind not talking? Okay, it's quite distracting when I'm trying to teach. Okay, so we have xi is 1 plus I over n. Now we need to find f of xi. So f of xi is equal to, well, f, and instead of x we substitute xi. So it will be 3, 1 plus I over n, and then we got the minus 1. Okay. Now we can simplify this a bit to make things easier for ourselves. So we have 3 minus 1, that will be 2, plus 3i over n. Okay. So that's our f of xi, which is the height of the rectangle. Okay, so what we want to do now is substitute everything into that Riemann sum, take the limit, and then we get our answer. So the area will be the limit as n goes to infinity, the sum from I equals 1 to n, f of xi, that's this 2 plus 3i over n, and delta x, that's 1 over n. Please don't forget the delta x at the end. Okay, previously when I taught this, many students left out the delta x at the end, and then everything else was wrong after that. Okay, please make sure you have everything in place. Okay, so this will be the limit as n goes to infinity, the the sum I equals 1 to n. Now we can distribute that delta x inside. So it's going to be 2 over n plus 3I over n squared. Okay, at this point we can expand the sum into individual terms and then take any constants out of the sum. So this will be the limit as n goes to infinity, 2 over n, the sum I equals 1 to n of just 1. So we took the constant out, so we're just left with 1 inside. Plus 3 over n squared, the sum from I equals 1 to n of I. Okay, so all the constants we took out, we're just left with the R terms. Now, for each of these sums, we can replace them with the closed form expression. So these ones over here. This one I'll leave for you to find out. Okay, so quick Google, you'll see what it is. So the reason I do that is if you do a little bit of research on your own, you remember it better. If I just write it down and you write it down without thinking, you forget it in an hour. If you have to look it up yourself, better chance that you remember it. Okay, we will only go up to r cubed. Okay, you don't need to know r to the 4 or anything like that. Okay, but the sum of I, that's n plus 1 over 2. So we can make that replacement there. So here we have the limit, n goes to infinity, 2 over n. This one we can replace with n, that's easy enough. Then we have 3 over n squared. This one we can replace with n plus 1 over 2. Okay. If this was the sum of r squared, you would replace it with the r squared formula. Okay, it's not so difficult to remember. Okay, now, before we take the limit, please make sure you simplify as much as possible. If you try to take the limit now, it's going to just be a big problem. Okay, so simplify first as much as possible, then take the limit, and then you'll get your answer. So the limit, n goes to infinity, 2n over n, that's just 2. And then we have 3 over 2n, and then n plus 1. Okay, we can simplify this a bit more. So here we have the limit, n goes to infinity, 2 plus 3 over 2 plus 3 over 2n. Okay, so this is what I mean by simplify as much as possible. We have individual terms, whether they have an n at the top, n at the bottom, that's not so important here, but we can't have products like this. So n plus 1 over n, we don't want that. We want individual terms so that we can take the limit. Okay, so if we do take the limit, what happens? 2, that stays the same. 3 over 2, that stays the same. But here we've got an n at the bottom. If we have an n at the bottom and we're taking the limit as n goes to infinity, the denominator will get bigger and bigger, the fraction will get smaller and smaller, so this goes to 0. Okay. If you get to this stage and you have an n in the numerator, you've done something wrong. Okay, so please make a note of that. At this stage, when you fully simplified, you should only ever have n in the denominator. If you have it in the numerator, go back up a few lines and see where you went wrong. Do not continue because it's going to be wrong and just problems. Okay, please make sure all your n's are on the bottom. It may be n, it may be n squared or n cubed, anything like that. You should never have n in the numerator. Okay, so please write that down. Okay, so we took the limit and then we left with 2 plus 3 over 2. So that will be 7 over 2. Okay, and then that's our final answer for the area. Okay, 7 over 2. It is an area, so you can put units squared if you want. Like I said before, if you're doing physics, the units are very important. For the maths, it's not so important. Okay, but if you want to write units squared to stay the same with physics, that's fine as well. Okay, let me give you some homework problems. So these homework problems will be due Monday, not Thursday. Okay, so you've got the weekend to go over them. But if you do want to come to my office today or tomorrow to go through the homework, that's fine as well. But officially due on Monday. Okay, so for all of them, it's finding the area under the curve, given the function, and the interval. Okay, so find the area under the curve. Okay, number one, f of x is 2x minus 1 on the interval 3, 5. Number two, f of x equals 3x plus 2 on the interval minus 1 to 1. Okay, number three, f of x equals x squared plus x on the interval 0, 1. F of x is equal to 2x minus x squared on the interval minus 1 to 1. Last one, okay, so this last one, you're not going to be tested so much on this. This is more of a bonus problem. So for class test 2, there will be a couple bonus problems for you to try. You don't have to do all of them, just like a couple you can do, and then that will be added onto your marks. Okay, so something like this will be in the list of those bonus problems. So that will be 2x cubed minus x squared plus 1 on the interval 0 to 2. Okay, so if you do want the bonus problems, it will be something like this. Okay, so that will be for your class test 2. Okay, so with those bonus problems for the top students, I know you could probably get 100% for that. If you do get over 100%, those extra marks will then be carried on to the next test. Okay, so you can't get like 105%, I will carry that over. Okay, so there were students that got 85, 75, and so on. If you do have extra time and you do all of the bonus problems, you could get more than 100. Okay, but then that will be carried over. Okay, so these 5, they will be due by the time we start the lecture on Monday. Okay, so you can email me, you can hand in your problems on paper, so some students do that. You can do it during the lecture, or you can hand it in when I'm in my office. Yeah, so that will be for Monday. Okay, any questions on this? Yes. Yeah. Sorry? Sorry, which one? The example. Okay. Yeah. Fourth step over here. Yeah. Oh, one above. Yeah. Sorry? Okay, so for here, we have the sum from I equals 1 to n, 2 over n plus 3i over n squared. So the first thing I did was write it as 2 separate sums. So we have the sum from I equals 1 to n, 2 over n, plus the sum from I equals 1 to n, 3i over n squared. Okay, so I just split it up into the 2 sums. Then all of this, there's no r terms. So it's a constant with respect to r. So what we can do with the sums is we can take it out. So here we can take it out of the sum, and then over here the 3 over n squared, that's also a constant. So we can take it out of the sum. So we can write this as 2 over n, just a constant. And then we have the sum, I equals 1 to n, of just 1. Because if we take it out, we're just left with the 1 there. Okay? plus, and then the same thing with the other term. We've got the 3 over n squared, it's a constant, we take it out. So 3 over n squared, the sum I equals 1 to n of I. And then I just look at this as one thing, and then I look at this as another thing. If we go back here, so the sum of 1, that's this bit here, I can replace that with n. So I just make the replacements. So that will be 2 over n times n, plus 3 over n squared, and then here, the sum of I, that's n plus 1 over 2, I just make the replacements as well. So here I make the replacements, n plus 1 over 2, and then that gets us back to that step there. Okay, so it's just simplifying until we have the sum in simplest form, and then we go back here, and then we just replace it. So whatever that sum was, like over here, we replace it with whatever's on the right. Okay, and then it's the same thing for r squared, so you need to look that up, and then the same thing for r cubed, I provided that one there. Okay, so this r squared one, it looks fairly similar to the sum of r, so please don't mix those up. Okay. Okay, and then the 5 questions for homework. Any other questions for the homework or anything we did today? Yeah. Go back. Yep.
How did you simplify the 2 plus 3 over 2
So here. So this n, I'm on this line over here. So this, it'll be better if I point here. So this n and this n, they cancel, and I'm just left with the 2. Over here, I've got an n and an n squared. I cancelled one of them, and then I'm just left with an n in the bottom.
How did you get 3 over 2 plus?
So the 3 over 2, so n over n, that's 1, that gives me this. And then I have 3 times the 1 over 2n, so that's the 3 times the 1 over 2n. So here you could write it as 3n over 2n. So that's the 3n over here over 2n, 3n over 2n, 3 times 1 over 2n, 3 times 1 over 2n. Okay. Okay, so it's just this bit here, that will then cancel. Okay, and then you're left with the 3 over 2. So here, that and that cancel there. Okay, so whenever you have brackets like this, over a single denominator, you can split it up into the first part and then the second part. Okay. And then that goes for all of the other calculations. So you expand the brackets, you'll get a single denominator, and then you can split it up. Okay, so always from here to here, always split it up into individual terms. Okay, any other questions? Okay, any questions on the antiderivative stuff? Everyone's still all right with that? Okay, so that will be it for today. If you want to meet me privately afterwards, here or in my office, please just come through and I can help you out. Okay, then I'll see you in the tutorial. Remember that you need to hand in your tutorials by the end of the session to the tutors. Okay.